All right, today we're going to do something a little different. We're not just looking at a math course, we are going to crack the code on the very first real challenge that almost every single engineering student has to face: matrices and calculus. And let me tell you, this isn't about memorizing formulas. This is about learning how to think like an engineer. So that really is the question, isn't it? How do you build an engineer? Do you just load them up with textbooks and formulas? Well, the answer that's kind of hidden inside this course material, it suggests something way, way deeper. It's really about forging a whole new way of looking at the world. And it all starts with a challenge like this one. What we're looking at here is a question bank for first-year engineering students. Now, I know it looks intimidating, maybe a little dry, but this is the gate. This is the first hurdle, and today we're going to find the keys to unlock it. At first glance, this thing looks like a massive, terrifying list of problems. But it's not. I want you to think of it less as a test and more like a map. It's a map that, if you just know how to read it, shows you exactly how to succeed, not just in the class, but in developing the mindset you're going to need for your whole career. And what's really wild is who this course is for. Look at this list: computer science, IT, AI, electrical, mechanical. We're talking about pretty much every major field of engineering. This isn't just some random class. It's a shared rite of passage. It's the fundamental language that all of them have to learn to speak. So yeah, on the surface, it looks like just a list of questions. But there is a deliberate, hidden architecture going on underneath it all. A structure that's been designed from the ground up to build very specific thinking skills. The secret isn't just solving the problems. It's understanding why they're designed the way they are. So to figure out that design, we need a decoder ring. And luckily for us, the document itself gives us one. The key to this entire blueprint comes from a famous framework in education, and once you see it, it changes everything. And here it is. It's called Bloom's taxonomy. This is the secret playbook. It's basically a way of sorting how we think into different levels of complexity. See, educators use this to make sure they're not just teaching facts you can memorize, but that they're actually building up some serious problem-solving horsepower. The easiest way to think about it is like a ladder. You start at the bottom, right? Level 1. That's just remembering. Can you recall a fact? Then you climb up to understanding it. Then you have to apply it, then analyze it, and finally, all the way at the top is level 5, evaluating. Using it to make a judgment in a really complex situation. Every step builds on the last. And this right here, this is where it all clicks into place. The exam is structured around those levels. Just look at the breakdown for the big 16-mark questions. There is only one question at that highest level: evaluating. That's the boss battle. This proves the exam isn't just a random assortment of problems. It's a carefully designed cognitive workout. Okay, so now that we know the rules of the game, let's take a look at the playing field. The course is broken up into 5 units, and you can think of each one as a different kind of training arena designed to build a very specific skill in an engineer's brain. So here are our 5 arenas: matrices, differential calculus, functions of several variables, integral calculus, and multiple integrals. Now don't worry, we're not going to sit here and do a bunch of math problems. What's important isn't the math itself, but what each of these units forces a student's brain to do. To show you what I mean, just look at the journey from the beginning to the end. You start in Unit I with matrices, which is all about understanding these abstract systems and structures. It's very theoretical. But by the time you fight your way to Unit V, multiple integrals, you're using all those concepts to do something incredibly real: calculate the volume of an actual object. It's a full journey from pure theory to physical reality. And these applications are absolutely everywhere. Take this question from Unit 3. This isn't just a math problem. This is about optimization. This is about finding the weakest point in a design, the most efficient route for a signal, or, yeah, in this case, the coldest spot on a piece of heated metal. This is what engineering is. So let's make that cognitive climb up Bloom's taxonomy really, really concrete. I'm going to show you 2 questions. They're from the very first unit on matrices, and they both use the exact same mathematical theorem, but honestly, they are worlds apart in what they ask you to do. So here's the first one. It's a simple 2-mark level 1 question. State the Cayley-Hamilton theorem. This is pure recall. You either memorized the definition or you didn't. It's that foundational piece of knowledge, the first step on the ladder. Simple, but you can't do anything else without it. And then there's this monster. This is the 60-mark Level 5 boss battle question. It uses that exact same theorem, but look what you have to do with it now. You have to apply it, you have to analyze the structure of this insane polynomial, and then you have to evaluate the best way to get to the answer. You can't just remember the theorem anymore. You have to wield it like a tool to take apart this huge, complex problem. That is the jump in thinking this whole course is trying to create. So why? Why put students through all of this? What's the point of this whole demanding journey, from just remembering something to being able to evaluate it? Well, it's all about building a toolkit that's going to last long after you've forgotten the exam itself.
At the end of the day, the exam is just a simulation. It's a practice run. It's a controlled environment designed to forge the mental tools you're going to need for the messy, unpredictable problems in the real world, the kind that don't come with a neat little question number attached.
The document even tells you what those tools are. They call them course outcomes. These 5 points right here, these are the real trophies you get for finishing the course. And notice they're not about math topics. They're about abilities, applying algebra, finding extreme points, solving practical problems. These are the skills of an engineer. And this is no accident. You've got 5 units, and they're each designed to build one of 5 core skills. This is the foundational toolkit. Everything else in an engineering degree gets built right on top of this. It all starts here. And it all leads up to questions just like this one from the very last unit. After weeks and weeks of abstract math, a student can now look at a simple equation for a sphere and, using the tools they've built, they can calculate its actual physical volume. They finally completed that journey, all the way from an abstract idea to a concrete reality. Which brings us back to that one final thought. When you look at a document like this, is it really just an exam? Is it just a hurdle you have to get over? Or, when you understand that hidden architecture, is it actually the blueprint for a new way of thinking? The very first and maybe the most important step in the construction of an engineer.